Looks like folks are having some success joining us, so let's go ahead and get started. Today's webinar session is a portion of a webinar series that Imubit is doing this year around demystifying the broader topic of industrial AI. This session today, Nadav, if you'll flip to the next one, is called Demystifying Industrial AI from Mainstream Approaches to State of the Art. And today we're going really broad, discussing some of the major areas of AI and how some of the different industrial applications apply to them. We'll go narrower and narrower for our focus as we build through this webinar series, ending out with the final session, Demystifying Industrial AI, a taxonomy of process control and optimization, where we'll really dive deep into the full spectrum of AI as it applies to the closed loop optimization space. Next slide. A couple of things before we get started today. So some housekeeping items. This session is going to be recorded. The recording will be automatically emailed to anybody who is registered, so it'll pop into your email after the session. During the session, we invite you to submit any questions that come to mind using the questions console. You'll notice on the bottom right of your Livestorm application, there's an option for questions and chat. Please use the questions console specifically for questions that you want answered during the Q&A at the end of the event. The chat is more for logistics or technical items. If you're having issues seeing or hearing something, let us know in the chat and we'll get to you as quickly as possible. We're going to use polls, which are also in the bottom right-hand side of the console throughout to ask just a couple of questions about you guys and where you are. And with that, let's get started with our first poll question. And that's going to be, what role is everybody in that is joining us today? So I'm going to publish that, and you should see that now in the polls console. Go ahead and submit your vote. So it looks like we've got a handful of folks in process control, APC, and RTO roles, some folks in data science, a couple in process engineering. If you're in one of these roles that's not listed here, feel free to click other and then shout out your role in the chat. Awesome. So a good mix of traditional kind of OT technology, process control, APC, RTO, and IT style technology with AI and data science. Thank you to everyone who responded to this poll. Nadav, can you go ahead and go to the next one? So like I said, today's talk is all about demystifying industrial AI from mainstream approaches to state of the art. We've got Professor Nadav Cohen, who is also the co-founder and CTO of Imubit, here today to talk to you about this topic that he is so knowledgeable in. So at this point, I will hand it over to Nadav.
Thank you very much, Allison. So I'm delighted to be here and talk to you all about industrial AI, trying to demystify it a little bit, convey some of the scientific and technical meaning behind these flashy terms. There are, as Allison mentioned, going to be 3 parts to this series. We're going to start today with very, very high level description of the different types of AI. What do they mean? What can they be used for? And as we go along, we'll dive deeper and deeper and get more and more technical. But in general, obviously, we do not assume any prior knowledge on AI. Okay, so just before we start, a few words about myself. I am a co-founder and president and CTO of Imubit. My area of expertise is the mathematical foundations of AI. And specifically neural networks, which are the driving force behind modern AI. Pretty much all the breakthroughs in AI over the last 15 years or so are due to neural networks. I am a professor of computer science, spent some time in Princeton, computer science, mathematics, PhD in computer science, master's in computer science, and originally electrical engineer and mathematician. I was fortunate to receive several recognitions for my contributions to the foundations of AI. I was the 4th person in the world to get a Google Doctoral Fellowship for contributions to the field, one of 11 people to get a Research Scholar Award, and recently received what some regard as one of the most prestigious scientific prizes in Europe. Besides the academic record, I have about 2 decades of experience applying AI to industrial systems. So for the last 8-9 years, it's been to the process industries, and before that in other industries like aerospace, which are obviously very different, but they do share some commonalities, specifically in terms of how critical they are and how important it is for the algorithms to be robust and reliable and explainable. So combining mathematical theories with real world tangible value has been a passion of mine throughout my entire career. All right, so let's now move to talk about AI. Obviously needs no introduction these days. We hear about it all the time. And it's being used in the process industries in various ways. Here are some examples. Predictive maintenance. You could use AI to predict when equipment's going to deteriorate or foul. You could also try to use it to forecast demand and make decisions based on these forecasts. You could use it in upstream. This is in the case of oil and gas, but other industries are analogous applications. So for example, for analyzing data, analyzing images, AI is used for that. And a more recent line of applications is assistive tools based on generative AI models. Just like in many other industries, productivity can boost by employing these large AI models. Now, maybe the most important takeaway from today that I'd like you to have is that AI is not a well-defined term. Okay? Saying AI is almost as broad as saying technology. And I believe that a few years from now, when people or a person or a company says that they implement AI, it'll be interpreted as broadly as saying that they implement technology. It's just too general of a statement. Okay? The question is, what kind of AI is in play? And from a professional standpoint, there are different types of AI, and they vary wildly in terms of how powerful they are and how complex it is to implement them. And so they're just different frameworks that have different names and are treated very, very differently by experts. And so the most basic framework is known as supervised learning. Then there are various other more advanced frameworks. Somewhere in the middle, there's a framework known as self-supervised learning, more frameworks, and on the higher end, there's a framework called reinforcement learning. The vast majority of AI applications in general and in industry are on the lower end. And on the higher end, there's a lot of unrealized value. Allison?
All right, for our next poll, we're going to ask all of you, where are you along your AI journeys? And so that poll should be visible to you now. All right, Nadav, we've got a few folks that are at the very beginning and looking to learn more. Actually, now the majority is flipped to we've implemented some AI-based optimization. And it looks like we'll give folks another couple seconds before I round us out. All right, we're looking at about 40% that have implemented some AI-based optimization, about a quarter with the very beginning looking to learn more, and with the remainder being in the we know we need AI, I want to explore, and then just a couple currently using AI and loving it. Thank you all for participating in the poll.
Okay, thank you, Allison. So I think it's an excellent mix. We try to address all the different levels of experience. Today, we're going to be mostly high level, so that it will be, I think, very appropriate for newcomers. For those that have more experience in AI, I'm hopeful that this will kind of help map things out, map the landscape, put things in perspective. And again, in the following parts of the series, we're going to dive deeper and deeper and really get kind of technical terms and the nuances of different types of AI solutions in the context of optimization. All right, so now let's talk about the three frameworks that I presented: supervised learning, self-supervised learning, and reinforcement learning. So supervised learning is a paradigm for designing a mapping from inputs to outputs. Okay, so the possible inputs could be, for example, minute-by-minute samples of some physical quantity, maybe temperature, pressure, something else, from some unit. Okay, so maybe 1,000 samples of temperature taken minute by minute from some unit of interest. And the possible outputs could be maybe one of three categories. A means that there's a problem, B means that everything's good, and C means that there's maybe a warning, a suspicion that something's wrong. A mapping would simply produce an output given an input. Okay, I feed into it an input, temperature readings, and I get a categorization as output. Okay? The traditional way to design such mappings is using first principles, using domain knowledge. Right? You are an expert on your unit, you know it best, and you can come up with a series of steps that will end up with a decision of how the unit is doing. And that's the traditional way to design mappings, and we, the industry, manage to do a lot this way. There are a lot of things that we can do with domain knowledge and first principles, but it turns out that there are problems that are very, very difficult to solve. In this way, it's very, very hard for a first principles model to capture all the different intricacies, all the different relevant factors. It just becomes too complex, right? The interaction with other units, the ambient conditions, the deterioration, catalyst change. This gets too complicated in many cases. And supervised learning offers a very different approach. Instead of designing a mapping through first principles, we choose one from examples. And what do I mean by that? We start by collecting a big class of possible mappings. It's usually a parametric class of mappings, so it has a lot of different mappings within it. So we have that, and we collect training data, which are examples of an input and output. So if the input would be the leftmost the plot that you see here, the output that should be produced is B. If it's the middle one, it's C, and if it's the right one, it's A. And so I collect these kind of examples that include an input and the output that the system should produce given that input. Then I take the mapping class and the training data, feed them both into what is called a training engine, which is simply a search for the mapping in the class that best agrees with the training data. Then I take that mapping, use it in the world. That is supervised learning. That's the most basic AI framework, most basic machine learning framework, and a vast amount or a vast proportion of AI applications falls into this category. It's this framework, supervised learning. Moving on to self-supervised learning. Here, what we would like is to design a predictor of sequence elements. What do I mean by that? I design a function that intakes a series of elements, x1 to xt. You can think of them as temperature readings. And it predicts the next element, xt plus 1. So, for example, I feed it temperature readings from the last few hours, and it will predict the temperature in the next minute. Okay, that would be an example. And I realize this predictor using supervised learning. So I learn this predictor from examples. That means that I define a big class of possible predictors, and I collect training data. This training data is typically taken from historical sequences. I just chop off a set of elements, as you can see, and that would be my input, and the corresponding output will be the next element that comes right after this series. And I do the same in other points in time, and that gives me other examples. And so I collect many of those examples and feed them into a training engine, which searches for the best predictor in the class, or in other words, the predictor in the class that best agrees with the training data. Then I take that predictor, use it in the world. Okay, so on the face of it, this is just a special case of supervised learning, but it turns out that this paradigm is very, very powerful. And actually, the main engine behind each and every one of the large language models that many of us use, the main engine is a self-supervised learning engine. And over there, what's being done, at least on the textual side, it's a predictor that gets a sequence of text tokens and predicts the next token. Okay, so you can think of it as a predictor that gets a series of words and predicts the next word. And it's trained over the entire internet, or at least the public, significant portion of the public internet. And then when you converse with this model, you give it a prompt, you feed in some text, and then that model predicts the next word. Then it takes the word that it has predicted, puts it as part of the context, predicts the next one in line, and the next one in line, and the next one in line, and that way it generates a textual response. Okay, so self-supervised learning is a very, very powerful approach. However, it's still a special case of an approach that's much more powerful, and that's reinforcement learning. In reinforcement learning, we're not designing a mapping or predictor. We're actually designing a controller that operates in a dynamic environment. Okay? So you can think of, like, maybe the simplest example is one of these robots that clean rooms or offices. Okay? That robot would have sensors through which it can sense the environment. It has motors, so it can act, it can move, and it's trying to achieve some long-term goal, which is to clean the office or the room. And if the office or room are empty, then it's easy, maybe. But if there are people there and things are dynamic, coffee's being spilt on the floor, then it becomes more challenging, and the robot needs to somehow adapt to evolving conditions, somehow realize a strategy in order to achieve a long-term goal. Okay, so that's the example. And formally, the reinforcement learning framework works as follows. The controller observes a state. That's a description of the environment status. So in the case of a robot, it'll be its sensory readings. Then it takes an action. Okay, it acts. So in the robot case, it'll be kind of commands to its motors that translate to movement. And then it receives a scalar, which is called a reward, and that's an indication of the goodness in the environment status. So in the robot case, if the room is cleaner, the reward could be +1. If it's dirtier, it could be -1. And if it's the same, it'll be 0. This is all one single iteration, state, action, reward, and it repeats again and again and again, and the controller's objective is to maximize the reward over time. And this is a very, very general framework. The controller is required to handle the dynamic environment and adapt, realize a long-term strategy in order to achieve a long-term goal. Yeah, so it's a super general problem. You can think of our lives basically as a reinforcement learning problem, right? We have senses, we can sense the environment. We have muscles, so we can move, and given a definition of a reward, maximizing that over time would be a reinforcement learning problem, right? So if the reward is, happiness or money in the bank, maximizing that over time is a reinforcement learning problem. It's a very complex one, but it is a reinforcement learning problem. All right, so an important note is that conventional methods for reinforcement learning rely on two fundamental assumptions. The first is that you have an accurate model, an accurate mathematical model of the environment. And the second is that you're allowed to conduct trial and error. So in the case of the robot, it'll mean that I have a mathematical model of office rooms, maybe, and I'm allowed to do trial and error. So the robot will start off not being very effective, but over time, it'll learn from its mistakes and it'll improve and improve and improve until it becomes very effective. And so these are the two fundamental assumptions underlying standard RL methods. In terms of applications of RL in other domains, here are some examples that are fairly well known. computer gaming. RL has reached superhuman level performance in computer gaming. It beat the world champion at Go. It's a relatively famous example. Google DeepMind. There's actually a movie about it on Netflix. It's a reinforcement learning agent that learned how to play Go and beat the world champion. So in these two cases, they are obviously impressive, but I think you can imagine that it might not be that difficult to satisfy the two fundamental assumptions. Specifically, having a mathematical model of a game is relatively easy, and so is conducting trial and error. One of the few very well-known examples in the real world is autonomous driving. Okay, and over here, in order to satisfy the two fundamental assumptions, a lot of resources were invested. Okay, a lot of very smart people developing mathematical models of roadways, and a lot of test cars with a lot of test drivers doing trial and error. And so, for example, if the algorithm wants to divert from the road, drive off the road, then the test driver would grab the steering wheel, the algorithm would get a reward of -1, and that way it conducts trial and error without actually crashing the car. So a lot of resources were invested in order to satisfy these two assumptions. Now, if we think about the process industries and what kind of opportunities RL could give rise to, then the possibilities are basically endless. Okay? Some potential applications include optimizing your processes. This is actually a new category of applications that has the name AIO. Allison will discuss this towards the end. AI optimization. Second potential application are decisions around transportation, transporting materials and pipelines, railroads, etc. And you could also imagine using RL in exploration. Basically, any decision-making problem, RL could solve for you if we had perfect RL. Okay? And unfortunately, we don't have perfect RL, and there are significant challenges. Typically in the process industries, the environments are very, very complex, very, very difficult to accurately model them, to have an accurate mathematical model. And trial and error is often not really an option. It's either too dangerous, too costly, or both. Okay? And so we are at a point where none of the two fundamental assumptions hold. So we can't use standard RL methods. And that's a big problem. So are we at a dead end? Probably not, otherwise we wouldn't be here. The key to overcoming this challenge is data. Yeah, I was told in one of my first days in my PhD is that the only thing better than data is more data. And so I would always recommend, no matter who you are, if you have the option to record data, please do so. Even if you don't know what you're going to do with it, you might be surprised at the value that it could give rise to in the future. And it is becoming more and more common to record data in the industries. Sometimes regulation even requires it. And that recorded data paves way to a new approach for RL, and that is to use self-supervised learning for learning a model of the environment. Okay? From potentially years of data, you can learn a model of the environment that captures intricacies going way beyond what a person's mental capacity can capture. And then taking that model, you apply trial and error, you run pretty much standard RL, but you do it over the learned model. So it's virtual. And safety and cost are not really issues, right? Safety concerns are basically non-existent, and the cost is just a compute. It's negligible. And so through this scheme, you can apply RL and learn a controller, and then apply that controller to a real system, but the learning itself is done offline. And this is not some kind of a idea or proof of concept. This is actually being used for process optimization as we speak across dozens of plants around the world. This is Imubit's Optimizing Brain. And what happens there is that there is a controller, which is a foundation neural network. I'll say a few words about this in a moment, and in the next parts of the series, we'll talk a lot more about this. But the controller for now is a foundation neural network. We have an environment, which is the plant. The controller observes the state, the current conditions of the plant, the process conditions, and it drives actions, manipulated variables on a minute-by-minute basis. And when the controller is on, it maximizes a reward, which usually reflects the margin. It just uplifts the margin. That reward could depend on constraints, process constraints, upper and lower bounds, things like that, and also on different parameters that determine trade-offs like market prices. These are all part of the reward, and they could be changed in real time. Foundation neural networks, I promised I'll say a word about that, so it's actually going to be a slide. So these are models that are state-of-the-art in learning functions from data. This is happening in practice. As I said, pretty much all the major breakthroughs in AI over the last 15 years are thanks to neural networks, and more specifically, they're thanks to foundation neural networks, which are very large neural networks that are end-to-end in the sense that when you implement a solution, you drive the input to the neural network, and the neural network gives you the output. The neural network is not just one subcomponent of a larger system, it is the system. That's what characterizes foundation neural networks. And alongside this practical success, there are also mathematical theories that prove the superiority of these models. And these are some of the works in the field that I was fortunate to be a part of and actually got the Google Fellowship for. And I'm not going to get into the mathematical theories, but I will say in a nutshell that these models have universal capacity in the sense that they can express pretty much any reasonable function. And so they allow you to introduce only those first principles of which you are confident. You don't have to build an entire first principles model and then tweak some parameters there. You can focus on the first principles of which you are certain, like mass balance, volume balance, and only introduce those, only use those to guide the learning. Okay, so this is really in a nutshell. We're going to talk a lot more about this in the next chapter in the series. And for now, I'll continue. So the closed loop AI optimization, how is it implemented? Let me just connect this to the scheme we saw earlier. I start by learning a model of the system. It's a foundation neural network. I use years of historical data to learn a foundation neural network, learn a system model. Then I take that system model and train on top of it a controller, which is also a foundation neural network. It's trained through reinforcement learning, millions and millions of scenarios, millions and millions of trial and error situations. The amount of experience that the controller gains during this trial and error process is equivalent to tens of thousands of years of human time. Okay, basically every point in history under various configurations of market prices and process constraints, the reinforcement learning controller learns how to operate in such conditions. All of this, learning of the system model and the reinforcement learning, all of this happens on the cloud. Yeah? And it's usually an overnight process. It's running on massive compute, GPU farms, but it's an overnight process. And then I take that controller and apply it to the true system. Okay? Minute by minute basis for real-time control and optimization. This solution has been implemented in various plants in the industry. We have over 90 closed loop applications, a lot of them in refining, but also in other spaces like cement, chemicals, calcining, in upstream. This is kind of a small subset of our current client base. We have a whole lot more. And we sometimes operate on top of APC, sometimes without APC. If APC is there, advanced process control, then it's even better. You'll get more value if you run the optimizing brain on top of it. If you don't have the APC, that's also fine. And we're going to talk a whole lot more about the exact relationship between the optimizing brain and reinforcement learning, between that and APC. Okay, so where's all this going? It's going in a direction where it's not going to be Imubit, or not just Imubit, that can develop, monitor, maintain, and deploy the optimizing brain, but you will be able to do so as well. And actually, some of you are doing this already. Okay? Whether you're in planning and economics, process controls, process engineering, operations, anybody could develop their own optimizing brain. Okay? You need to know your domain. You need to know the problem that you are trying to solve, but you don't need to design the control strategy. You don't need to take care of the how it's being done, only the what should be done. And we have an entire industrial AI platform that takes care of all the machine learning for you. And there's a lot of research going on, a lot of science behind this platform, specifically explainability. It's not enough to have powerful neural network models. It's very important that they be understandable by the different personas. A lot of tools for explainability, a lot of tools for automating the model development. This is an area of AI called AutoML, automatic machine learning. And so in this journey, we begin with Imubit personnel working with you and ramping you up on the technology. But over time, typically customers become more and more independent, and some of our clients are already very independent. Those have been those that were keen to make progress in this journey of being independent. And at the end of the day, you'll be able to do all of this yourself and apply reinforcement learning, which is severely kind of underutilized in the industry right now. And the value potential is something that is unprecedented. So with this, I'll conclude. And I think we could go to Q&A.
Yeah, thank you so much, Nadav. We've got a flurry of questions that have rolled into the Q&A, and a lot of these questions focus, at some degree at least, on Imubit's solution in contrast with traditional APC and RTO technologies. So I was wondering if, before we dive into some of the specific questions around this, if you could give us a response to the more holistic question of how does Imubit differ from some of the legacy technologies out there, as well as some of the hybrid approaches that you're seeing in the market?
Yeah, okay. So first of all, my kind of first answer would be that that's the entire purpose of the next, the continuation of the series. Next time, we're going to talk about the differences between neural networks and hybrid models. And after that, the differences between reinforcement learning and model predictive control. What I can say at this point, in very high level, is that in AI in general, okay, the solution, any solution, is determined by there are two aspects that define an AI solution, and that is the AI framework that is at play and the AI model that's being used. Imubit operates in reinforcement learning, that's the framework, and the model are foundation neural networks. The difference between Imubit solution and hybrid models is on the model front, foundation neural networks versus what some of our competitors refer to as hybrid models. There is a difference there. We're going to dive deep into this. I would say that the main difference in philosophy is that traditional hybrid models start from a first principle model and then learn components of it, whereas the foundation neural network approach starts from a data-driven play, where you learn a foundation neural network and then you only introduce specific first principles that you are confident in. You introduce them to guide the learning. Okay, that's the difference in approaches. It's not that one is necessarily better than the other. They are suited for different problems. And from our experience, the very complex problems, typically multi-unit and plant-wide problems, are very, very difficult to model with first principles. And in these cases, oftentimes, data-first approaches provide more options. So that's that. And the other thing is APC versus optimizing brain. That's basically reinforcement learning versus a very traditional paradigm known as model predictive control. And the advantage of reinforcement learning comes into play when your model is imperfect. If your model is perfect, model predictive control, or close to it, then model predictive control is a great approach. Otherwise, if your model is not, then reinforcement learning has a lot of advantages. And again, for some problems, it's fairly easy to come up with a very, very accurate model. And over there, model predictive control can work excellently. For other problems, usually the more complex ones, models are inaccurate. And reinforcement learning brings a lot of benefits there. So that's in a nutshell. And again, parts 2 and 3 will dive deep into these topics.
Thanks, Nadav. So related to the APC and RTO conversation, there's a couple questions about economics. If you have any comments on that, you're welcome to add them, and I can also take some of the answer.
Mm-hmm.
So how do Imubit solutions compare with an APC or RTO implementation in terms of return or in terms of economic benefits?
Let me just open the question. Okay, so you're going to be reading them out, Allison. How does it compare in terms of benefits?
Mm-hmm.
Yeah, so in those deployments that have taken place, the added value of Imubit is on top of APC. Usually, if APC is there, we measure our value on top of APC, and I guess it depends on the case, but the return is pretty significant. Allison, I don't know if you want to share more details.
Yeah, my comments are really just it's a complex question. So you've got comparing Imubit's value delivered in a scenario where maybe there's no APC RTO. You've got whether there's a little bit of APC or maybe it's full on APC and RTO. And it's not necessarily apples to apples, because in an ideal situation, Imubit is going after the problem that you haven't historically been able to solve with APC and RTO. So going after the really complex nonlinear system dynamics. And so you're measuring off of a large potential. There's also in a return calculation a time element. So if you're measuring return over time, that time denominator, if we can deploy Imubit as a model in say 3 to 6 months, then you'll get your return faster, and so that benefit calculation looks better. So there's a lot of variability in that answer, obviously. But one of the big components of Imubit's customer success process, and the whole, before you actually implement the model, we do what's called an optimization workshop, where we have a team of former refining economics and planning engineers that go in and do a really robust benefit analysis before you even implement the project. So you'll have a good idea before you go in of what the potential benefits would be of using an Imubit solution versus whatever you've either got already or whatever else you're investigating.
So just to add on that, APC is usually viewed as a control solution and less optimization. And so Imubit's optimizing brain is an optimization solution. And also, as opposed to RTO, which usually operates at a lower frequency, like every hour, every few hours, Imubit's model runs on a minute-by-minute basis. So it does apply it's not an apples to apples. These are different problems. And maybe, ironically, the more value is being generated by APC and RTO, if they're there, the more added value the optimizing brain will yield. That's from our experience.
Thanks, Nadav. So the next highest voted question is, how do you best deal with unmeasured but important variables and also potentially sensor drift or equipment degradation that also could impact model relationships over time?
Yeah. Okay. Great question. So first of all, what I will say is that there is no magic in a data-driven approach, and AI is data-driven. The data quality matters, right? And first principles and domain knowledge allow you to deal with situations where the data is missing, where the information is not there, or the data is completely erroneous. And so a native part of our technology is the incorporation of first principles into foundation neural networks. We have patents on that, and that is an important factor. However, and this is very important to clarify, foundation neural networks, these kind of learning models, can pick up on things that might be very surprising to us if we come from a more traditional linear modeling background. For example, sometimes there's certain variables that you don't have access to, like the feedstock or things like that. But they manifest themselves, the information manifests itself in other variables. Like the dynamics of different controlled variables could be impacted by the feedstock, and the system model is able to pick up on that information and infer the feedstock from the behavior of these other signals. When you have a very powerful nonlinear model, it's able to do these things, and we see it all the time.
Awesome. So next question is the Imubit controller capable of handling interactions between different units in a chemical plant? So a multi-unit optimization kind of problem.
Yes, that's the kind of, that's a short answer. Yes. A longer answer is that this is actually the sweet spot of Imubit, to not confine itself to local control and optimization problems, but rather solve more global problems. So a typical controller would handle a number of, the number of manipulated variables will be 5, 8, maybe up to 10. The number of controlled variables, a few dozen, DVs also. The size of the optimization problem might be surprising, but oftentimes the limiting factor is the time it takes to train a controller. We'd like to keep it under 12 hours. And solving larger problems, first of all, it becomes more and more feasible as the compute power improves, which happens regardless of us. But also, you could build a hierarchy of controllers. And many of our clients have done this and have solved very large problems, multi-unit, using a hierarchy of models. So the answer is yes.
Considering that AI in Imubit's models is built with the existing plant data, how does the solution perform extrapolation and exploring new plant conditions without incurring any risks?
Yeah. Okay, so that's a loaded question. So when you learn from data, and this is true for AI in general, the whole point is to handle data that you didn't see in training, right? And it can be, kind of roughly speaking, partitioned into two types of two cases, right? One is interpolation, where you now encounter situations that you haven't seen, but there's somewhere in between. This situation is somewhere in between things that you have seen. So that's interpolation, and neural networks are exceptional at this, at interpolation. There are a lot of mathematical theories also that back this. I've done a lot of work on it myself, proving these things. And so that's basically the first and foremost, that's the great benefit of foundation neural networks. The second case would be extrapolation, where the conditions go beyond anything that you've seen. It's not in between conditions that you have seen, it's beyond. And so neural networks are superior to other models in terms of their extrapolation. There are also theories establishing that, but they're not perfect. There is no perfect extrapolation, because if there would be, you wouldn't even need any data. You could just extrapolate to everything. So there is no magic here. If you are encountering conditions that go beyond anything you've seen, first principles there matter more. So that's where you would like to incorporate the first principles into the foundation neural networks. And what I will say from our experience, and many of our models have been running for years, is that it's not very common that the units get into conditions that have nothing to do with anything seen in history. Things like catalyst change and stuff like that, you'd often be surprised at the amount of information that can be inferred from years of historical data, especially if it included a catalyst change. And so in these conditions, oftentimes the controller works well as is, or in some cases you need to collect new data. But if training from scratch requires at least 2-3 months of data, in these situations, it could be 2-3 days, something like that. And just to conclude this answer, besides everything that I've just said, there's a layer of software that you can configure that determines the operating envelope for the model, bounds for the MVs, and it could also define logic. In these situations, act this way, in those situations, act that way. So regardless of what the AI model wants to do, you have a layer of software that ensures predictable behavior exactly as you define it.
Thanks, Nadav. I'll give you a break on the next question. So this one is, how do you compare the time and cost of deployment of an Imubit optimizing brain project to traditional APC and RTO? So I'll answer that first on the time horizon. So we see Imubit in like the first model deployment at a new customer being deployed in closed loop by about the 6-month time horizon. You gain some efficiencies after that first one. And so subsequent model deployments are usually a bit faster. So our customers with 10, 15 models, their time horizon is more in that 3 to 6 month window. I'm not going to state the time horizon for a traditional IPC RTO project because that's not my expertise. So you can compare that with what you know to be true for those types of projects at your organization. And then in terms of cost, there's a lot of different elements of the cost of one of these projects. With Imubit, your subscription license cost is a known quantity going in year over year, and that includes the subscription services, which include all of the economic engineering and customer success, proactive model monitoring. And so that's built into the cost. It's known. There's not, other than the kind of one-time project services piece, there's not a heavy services component in subsequent years. So compared to traditional APC, which is known to be a services heavy technology, you can do that math as well. All right.
So just to add to that, some of our clients that are more advanced in their AI journey are gaining more and more independence and are able to do more and more themselves, and that also obviously impacts the cost.
Cost and timeline for sure. Okay, we've got a few minutes left, so we'll get through a couple more questions, and then if we don't get through your questions, we'll follow up with you via email and address those. The next question is, in RTO, it's typical to run a reconciliation phase of the data before executing the optimization. That's because the measurements don't necessarily respect mass and energy balances, and there could be gross errors. How does Imubit solve for that?
Yeah, so indeed, the data, the historical data, doesn't always respect physical laws like mass balance and things like that. It is because usually either measurement errors, things like that, or sometimes there's a tank in between. There are degrees of freedom in how exactly you define mass balance. This all comes into play in the experience. Okay? In the experience, the controller learns to deal with the imperfectness of the data, and you can incorporate into the learning of the system model. You can incorporate those first principles, and as long as the conditions and the behavior of these tags is similar to what it was in history, then from the controller's perspective, it's perfectly fine.
All right, the next question, I think we're actually going to defer to the next webinar. So question around including first principles, Nadav's going to go in depth on that in the next session. Does Imubit provide online retraining of the neural network to cover new operating envelope, or is it handled offline?
Yeah. So in principle, in reinforcement learning, it's perfectly possible. It's actually common to update the controller online in real time. Imubit took a product design decision for the time being, to not update the controller at all online. We did this so that you can test your controller offline using all of our explainability and AutoML tools. You can test it, then you feel comfortable with it. It's just a function. You apply it in the plant, and it does not modify itself at all. That's how it is today. If you want to update the controller, not a problem. Data is streamed to the cloud anyway. You just retrain overnight, you get a new one. But nothing's going to happen without your direct involvement and initiation. That's where we are today. In the future, I definitely foresee a situation where we will start modifying the controllers online, but we don't do that today.
Alrighty, the next question is the foundation neural network constrained to not predict behavior that's not physically possible? For example, increasing a temperature with the objective of decreasing pressure.
Yeah, so if you have highly accurate data and sufficient amounts, then this is all going to be learned. The purpose of the first principles that I mentioned, the incorporation of first principles into learning, is to deal with situations where you don't have sufficient data quality or quantity. And over there, you introduce these first principles, and there are templates on how to do this with a graphical user interface, and that way it's ensured. So yeah, this is done all the time. It's completely standard. It's a standard part of our process.
Okay, a fun question. Operators typically don't like black box models. How do we as Imubit demystify the foundation neural network models to provide better adoption?
Yeah. So there is tension between powerful AI models and explainability, in the sense that the most explainable thing is typically not the most powerful thing. And what I mean by that, like a linear model. Perfectly explainable, you understand everything, but it's limited, right? So by definition, by moving to advanced AI, and it doesn't matter if it's Imubit or something else, you're giving up on some degree of explainability. However, there is a lot that can be done. We have an entire team in our company whose sole purpose is to develop machine learning for explainability. And there are a lot of different tools that we provide. It's a never-ending pursuit. We're going to continue improving more and more and providing more and more explainability tools. But there are a lot of things that we provide in our platform. And the explainability, our view of explainability is not generic. We don't try to explain the neural networks in generic terms. We understand the personas. We understand you. Most of the people in our company worked for different companies in the industry. And our approach to explainability starts from who you are and what information you are looking for. And again, there's a lot that can be done. We have different demonstrations of our platform. We're going to see, Allison, what venue we provide to this audience and this crowd for getting insight into these tools that we provide. But it's something that is an integral part of our platform, and we will share it.
Thanks for that answer, Nadav. We've got a ton of other questions in the chat, but we're not going to have time to answer all of those online today. So if your question did not get answered, don't worry. We will follow up with you individually via email after this. Nadav, if you can toggle to the next slide. One last thing for today. So we mentioned that this webinar is part of this series. So we encourage everybody who engaged in the Q&A and who was interested in the topic to sign up for the subsequent webinars. And Nadav mentioned briefly AI-based optimization. So there is a new category in the process optimization and control space that's taking shape, and that's called closed loop AI optimization, or shortened AIO. So you can go to this URL here at imubit.com/AIO to learn a little bit more about that new category and how some of the different technologies are stacking up within that. So thank you all for joining today, and we hope you have a great rest of your day.
Thank you very much.